Okay, good morning, everyone. How many of you have started node voltage analysis? The videos. All right. So some of you. So beginning from node voltage analysis is where we are going to learn two of the most important techniques, node voltage analysis and mesh current analysis. So far in the course, the techniques that we have covered were based on Ohm's law, voltage division, current division, and then KCL, KVL, all of those comprised of some of the techniques that you learned in your prereqs physics classes. From now on, after voltage and current division, we learn those two techniques. These two techniques are based on Ohm's law and KVL and KCL. So oftentimes we'd have a circuit which has only one source. If it has one source, we try to see if the resistive network is reducible down to one single resistance. If we can reduce it to one single resistance, then we can use the technique where we find Req, apply Ohm's law, and then expand the circuit back up, right? That was homework number 7, right? Homework number 7. So you find Req, apply Ohm's law, and then solve for voltages and currents. But some circuits are not reducible, meaning the resistors are connected in such a way that we cannot manually or theoretically combine it into one single resistance. So there's no easy way to find Req, the total equivalent resistance. Also, there are cases where we have multiple sources in the same circuit. So if you have more than one source, whether they're voltage sources or current sources or a combination of both, doesn't really matter what, then we cannot find it by one single, by the Req method. The third case is if we have dependent sources, the diamond-shaped dependent sources in the circuit, again, we cannot use the resistive circuit analysis, the series parallel equivalent. So we cannot use those techniques to find Req. And so in those cases, we apply node voltage and mesh current analysis techniques. Okay. So before we talk about that, there is homework number 8, which is voltage division and current division. So let's take a look at that. And just once have any questions, we can get those answered. So let's see. So we stopped here last lecture, and we went through voltage division and current division. Voltage division applies only to resistors in series because the current remains the same. And current division applies to resistors in parallel because, of course, the voltage remains the same. So these two techniques are simply shortcuts. They simply allow us to skip one step. Okay. It seems like a very small thing, but when we are solving larger circuits, it helps to skip a few steps. So voltage division equation is given by VR is equal to VS times R over total equivalent resistance, Req. If you notice this equation, let's say Req was not part of it. What do you see here? Sorry, actually, no, that's the other way around. Not this one. If R1 was not part of the equation, what do you think this represents? Ohm's law, V equals IR. So VS over Req. I'm going to ask your physics professors to change your grade back. What does it represent? Current. But what current? The total current that's flowing in the circuit, because we have one voltage source and we have one Req that represents the total current that is flowing in the circuit. So we didn't have to apply Ohm's law to determine the total current that's flowing in the circuit. Hence, shortcut. So we simply take the equation, we find the ratio of R1 to Req, and you multiply it with the source voltage, that gives you the voltage across that specific resistor. Hence, shortcut. Does that make sense? Okay. And the same thing for current division. In current division, if we ignore R1, and we just have IS times REQ, what do we get? We get the total voltage that appears across those two nodes, the parallel nodes, right? So again, Ohm's law, V equals IR. IS is the total current that's coming into the parallel network. REQ is the total REQ of the parallel resistors. And so that gives us the total voltage in that circuit. And so again, if you apply current division, it allows us to skip that step. We don't need to find the voltage. All right. Let's see, lecture 7. Then let's open up our homework page. Okay, how many of you have started working on homework 8? How many of you are done with it? Okay. Any specific questions from anyone? Or any of the previous homework? Anything about 6 or 7 or 5, 4, 3, 2, 1? This one is rather straightforward because it's a simple circuit, similarly as the one that we have in the lecture slides and the lecture video. So I'm assuming that students didn't have too much of trouble with this. How about this one? Straightforward too. 3 amps being divided into I1 and I2. And then you had these two. So question asked here was the voltage division principle to calculate V in the figure. On a slightly related but separate note, if a question, whether it's on a quiz or an exam or a homework or anywhere else for that matter, if it asks the student for a specific method, you must show that method. Okay, again, methods or techniques or analysis techniques are all tools in our toolbox. We can use multiple tools in different manner to solve the same problem. Okay, but if it's asking you for a specific method, then you must solve it using that method. Otherwise, you will not receive points for that. Okay, the logic behind that is we are all governed by the ABET accreditation board, and so we are required to teach students certain things or certain topics, and then we are required to assess the students' understanding of those topics. So if I or if some other professor is asking you, okay, solve it using only Ohm's law, if you solve it using a different method, then we have no basis for assessment. We don't know whether the student knows Ohm's law or not. That's the logic behind it. So in this case, we can use different techniques to solve this, but if it's asking us voltage division, then we must apply voltage division. Okay. To apply voltage division, the resistors must be in series. What do we see here? We see that there is one 20 ohm resistor, and then the other two resistors, R2 and R3, are in parallel. So we must reduce the circuit such that we have two resistors in series. This was problem number, let's see, 2.38. So all we need to do is combine R2 and R3 in parallel. I'm going to call it R4. R4 is equal to the parallel combination of R2 and R3. And now I have two resistors in series. And hence now we can apply voltage division. Okay. So straightforward as far as problems go. Make sense to everyone? Right. Now, as part of this small standalone circuit, it seems very simple, very straightforward. But the application of voltage and current division comes when we have a large circuit. The large circuit could be anywhere from, I don't know, like 10 components to hundreds of thousands of components. And so if you have a large circuit and you have, let's say, for example, just draw some random circuit. We have some components here on the left. We don't know what's in there. Then we have a resistor. And then we have multiple other resistors this way and this way. So we don't know what's here to the left, and we then don't know what's here to the right. Okay, and we are only analyzing this small portion in the middle. And we wish to find, for example, we wish to find the currents going down here and the voltages that appear across these resistors. Okay, so we could break off this circuit if we know the current that's coming down here. Then we can apply current division right here to determine the voltages. To determine the currents. Okay, the voltage division and current division are used as shortcut techniques when you're analyzing large circuits, and that's a real life case where that's possible. So in this case, let's say this is IRA, this is IRB, and this is IRC. And we previously may have calculated IRA. So in this case, we are only applying current division to this portion of that large circuit. And we can say IRA would be the source current for IRB and IRC. Okay, makes sense. And similarly, if you combine, well, there might be a series connection of resistors, and we could find voltage in that. For instance, if instead of this being one resistor, let's say there were two, right? Let's say there were two resistors. So you'd have a plus minus here and a plus minus here. IRC coming down this way, current remains the same, series circuit, voltage gets divided. Once we calculate the voltage, let's say, let's call this VA, let's call this VB. VB gets divided across those two resistors or between those two resistors. So VB will be the source voltage for the series resistors. And then you could apply voltage division and one-step calculation to find the voltages across those two resistors. Right. So let's take a pause, think over all of that. Let me know if you have any questions. Questions at all? Did all of that make sense? Applications and everything. Okay. Let's give it 10 more seconds. Current division principle to calculate the value of I3. Okay. Okay, so that was the problem number 3 for voltage division. This is problem number 4. That's the last problem in this homework. Current division. What do you think? Do we have to do anything? So, sorry, I just switched here. So here we had to combine the resistors R2 and R3 in order to obtain a series combination. So what do we have to do in problem number 4? This is a conceptual question. It's testing your knowledge of concepts. So we have parallel resistors and sorry, what did you miss? So we reduce it. So that's a good point, similar to the previous one. Any other notes? Yes. Yes. So you're absolutely right. So here, if you take a look at IS, actually, let me copy it over there. Copy to the notebook. And so you are also correct. We can reduce it and we can find current going through there. We can find the voltage and then find the current that way. But if we wish to apply current division, we can do so directly. Let's write this down. This is problem number 2.39. Okay. So 2.39. So in this, if we refer to the concept of an ideal voltage source and an ideal current source, the properties are that an ideal source will supply its rated quantity at its terminals. Meaning if IS is flowing as shown, it's going from bottom to up. It has nowhere else to go except make a right turn and go through the 100 ohm resistor. So the current flowing through the 100 ohm resistor is IS until it gets to this node. And when it gets to that node, it gets divided. let's say it gets divided into I2 and I3. And again, so I3 comes through here, and I2 is also coming into the node, and then it combines to form IS again. So this again becomes IS. And so no matter how many resistors or components we have in series with that current source, up until the point where you have a node that separates out, it will always remain that same current. Same thing with a voltage source. If we have anything connected in parallel to a voltage source, then all components, no matter how many we have connected, will have the exact same voltage as that voltage source. So it does not get divided until after the node separates out. Until then, the current will remain the same. So even if we had 100 resistors all connected in series here in this path, they would all have the same current IS. Okay, and that's the property, that's the concept of a ideal current source. It supplies the rated current. And so in this case, this fourth problem on the homework is the exact same as the second one. So it's just testing the concept a little bit, but the problem is the same. You have current coming in, you apply current division, and you find the currents I2 and I3. That's it. So as far as other homework assignments go, this one's not that onerous or long. All right, let's take a pause. Let me know if you have any questions. If you want to solve this right now, you can do so. So if you have any questions, you can get those answered. So let's see. The same homework, right? So first one is a tutorial. The second one is the video solution with a question, and then 36, 37, 38, 39. So that's 36. That's 37. So 37 and 39, they are exactly the same, except you have a series resistor in the pathway. And then of course, 38 was the voltage division. Now, anytime you look at these homework, and students often ask me, sometimes they ask me, do I have more circuits for practice? My answer to that is all of these homework problems, they have lots of different kinds of circuits. Just because it asks us to solve it using one particular method does not mean we cannot use a different method, right? So if we wish to practice voltage division on this circuit, we can do so. If we wish to practice series parallel analysis, meaning reduce everything down to one single resistance and then solve it, we can do so. So the same circuit can be solved using at least 3 or 4 different techniques. We could also solve it using solely KVL and KCL. Okay, KVL, KCL, and Ohm's law. Repeated applications of KVL, KCL, and Ohm's law. And so the more practice we obtain using multiple techniques on the same circuit, the better we can get. That's the question, right? The specific lecture video. I am not sure because I'd have to look it up. I'll have to look it up. Okay, week 1 lecture video 4. Yeah. All right, so week 1 and then lecture 4. That's in here. Chapter 2, yeah. So it's still chapter 2 at the beginning. And then I believe node voltage begins in this lecture 5 video. Let's see. 3 goes up to, let's see, chapter 2, Thevenin Norton. Yeah, it goes mesh current analysis and Thevenin Norton. Okay. So how do you feel about homework 8? Doable? Any questions? Okay. All right. So then homework 9, which was what I was talking about. Let's go to our assignments list. And let's look at node voltage analysis. And some students did say that they have started working on this, right? So it's only 3 problems in here, but again, that's for more practice. I strongly recommend students take any circuit from any of the homework and try to solve it with any technique. Okay, and you should be able to, you should reach a point where you are able to obtain the same answers with any technique. Okay, so for this, what I'm going to do is I'm going to go into the lecture slides a little bit, and then I talk about this technique. All right, let's see. So here, okay, this is the one we want. And 12 also. Okay. I'm going to change the pages and everything later. So the concept that we want to understand is the concept of nodes, branch currents, mesh currents, and loops. Okay. So again, there's a separate slide where I talk about the 4. There's nodes, mesh, loop, and branches. Okay. So node is any junction point in a circuit where you have 2 or more components coming together. So here at B, at D, you have 2 components coming together. So whether it's explicitly marked with a dot, like a circle that's like shaded circle, whether it's a dot or whether it's just an angle of a line, it still is a node. Okay. So sometimes students, there is some confusion sometimes whether it consists of a node or not. If it's 2 components connected together, that is a node. It's a junction point. It's a meeting point of 2 components. So that's a node. That's it. Now, when you have 2 nodes, if it's connected by a wire, it's the exact same node. Okay. So you might think this is a node, and this A is a node. But if you start from the left, go all the way to the right, there's nothing but wire between those nodes. So if all we have are wires between those 2 nodes or those 3 nodes, then they are still the same exact electrical node. They have the same electrical potential, meaning all of this is one single node. Okay. And so this concept is something to retain. So you're able to recognize and analyze, set up the circuit very quickly right at the top. Okay? Identifying the nodes is very critical. So oftentimes I see students make errors where they have multiple nodes and they're connected by a wire. Instead of taking it as a single node, they would take it as two separate nodes or three separate nodes. So again, I'm emphasizing anything that is connected by a wire is the same exact node, no difference whatsoever. So those are nodes. Anything that is connected between two nodes is a branch. Okay. Whether it's a wire or a resistor, capacitor, inductor, doesn't really matter. That's known as a branch of the circuit. So in this case, we could technically say this is a branch of the circuit, though we don't identify it as such. More importantly, here we have a resistor connected, and so we call that as a separate branch of the circuit. Okay, so that's one branch. This is another. This is another. And then this is another. All of those are branches of the circuit. So that's node. This is a branch. Also, anything that's in series is said to be the same branch. So here we have R3 is not marked. I'm going to mark it. This is R3. And R3 and R4 are in series, right? They are connected at a node, but there is no third connection at that node. And so if there is no more than two components at a single node, those two components are said to be in series. And so R3 and R4 are in series, and so is the voltage source and R1. They are also in series. And so technically, we can state that this circuit has only three branches. That's it. You have the branch on the left, which has the voltage source and R1. You have the branch in the middle, which is R2. And we have a third branch on the right, which is R3 and R4. And that's it. Does that make sense, Daryl? Right? And then if you have two branches that are coming together and it forms like a circle or a loop, well, forms like a circular pathway, circular connection, that's known as a loop. So technically, a loop can be comprised of a minimum of two branches. Okay, any two branches coming together can comprise a loop. And so here I could redraw this circuit with node C at the top, and I would have R2 in the middle, I have R3, I have R4, and I'm just redrawing the circuit in a different manner. And so from node C at the top to node A at the bottom, what do we see? We see that all of these are in parallel. The three branches are in parallel because they are all connected between A and C. And then between A and C, on the left, we have one loop. On the right, we have one loop. Because it forms a closed pathway. Anytime we have a closed pathway in a circuit, that's a loop. Okay. So loops are easy to, well, not easy. Loop is a closed pathway, meaning you start at a point, you go around the circuit, and if you are able to return to that same point without going back, then that's an electrical loop. A subset of loops is a mesh. So a mesh is a loop. But let's identify the loops in here. Okay. We have actually. This is loop 1. This is loop 2. What other loops do you see? If we start at A, how many other pathways do you see to return back to A? There's 2 that I identified. There's one more. Yes, outside of the circuit, outer loop. So if we start from A and we go progress the outside, we can still come back to A. So that's loop number 3. And there are a maximum of 3 loops in the circuit. So the special thing about loops is that it can contain other loops inside it. Okay, so L1 and L2 are inside loop number 3. So every circuit will have an outer loop. All circuits will have an outer loop, and then they'll have other smaller loops inside it. Okay, but a mesh is a special kind of loop, meaning it does not have any other loops inside it. So if you look at these 3 loops, L1, L2, and L3 are loops. However, a mesh is a simple loop that does not have any other loops inside it. And so meshes are L2 and L3 in this example. Okay, L2 and L3. And the entire concept of mesh current analysis is based on this, that a mesh is an electrical loop that does not have any other loops inside it. So it's a simple loop. Okay, whereas L3 is not a mesh. It is simply a loop. And that's it. And that's the difference between meshes and loops. Okay, loops are something we use when we apply KVL, right? We need to know all of the voltages inside the loop, and it works out to be 0. And that's why my head can't actually grasp how it actually works. I mean, I know it works. I also know how it's derived and everything based on law of conservation of energy. But if you sum up the voltages in L1, they'll be equal to 0. If you sum up the voltages in L2, they'll be equal to 0. And you sum up the voltages in L3, they will also be equal to 0. That's the beauty of KVL. Anyway, so for node voltage analysis, we need to identify all the nodes in the circuit. For mesh current analysis, we need to identify all the meshes in the circuit. Identifying meshes is rather straightforward, because you take a look at the circuit, our brains can immediately we visually observe it, and we automatically, it clicks in our brains. Okay, that's a loop. Nodes, we have to kind of train our brains a little bit. Does that make sense? So we need to get better at identifying the nodes in the circuit. Okay. All right. So the concept of node voltage analysis and mesh current analysis is based on KVL and KCL. The entire point of circuit analysis is to mathematically solve for the voltages and currents that appear in our circuit. In order to solve them mathematically, we need to write mathematical equations. In order to generate those equations, we use a variety of techniques. We apply KVL, we apply KCL, we apply Ohm's law. But some instances, we can't apply all of them separately. And so we combine them together and we apply them. So in node voltage analysis, we apply KCL to generate our equations. In mesh current analysis, we apply KVL to generate our equations. Okay. Again, these techniques are just so that we can generate equations. The more variables we have, the more equations we need. Okay. So if you identify the nodes in the circuit, speaking of node voltage analysis, then we have 1, 2, 3 nodes in the circuit. Well, actually, if we discount D, if we combine them in series, we only have 3 nodes in the circuit, right? The circuit as shown shows you A, B, C, D. But if you have a series connection, if you have 2 resistors in series, we can combine them and eliminate 1 node. And why would we do that? Because every single node is an unknown variable. So the number of unknown variables is equal to the number of equations. So if you have 4 nodes in your circuit, you need 4 equations to solve them. If you have 3, you only need 3. If you have 2, you only need 2. Make sense? Right? So again, using the same circuit as an example, we combine these together, and then we only have 1 node. Okay, but let's keep them separate for now, just so that we understand the concept, right? So what are we doing? What we are doing is, we identify a node in a circuit to use or act as a reference node. Again, this is node voltage analysis, nodal analysis. We are going to write KCL or current equations. And so we choose a reference node. Now, if you're taking the lab and you have used the multimeters to measure voltages, what do? We have 2 ends. We take the common terminal and we connect it to our baseline, a baseline measurement. And then we take the positive end and we connect it around the nodes so that we know what we are measuring, right? So it's important to understand, in most circuits, the negative end of the voltage source will be shown at the bottom, which is like kind of like right here. And this symbol right here indicates it's actually used for earth or ground. But in electrical circuits, it could simply mean a reference node. So if you see a symbol like this, which indicates ground or earth, it refers to it being the reference node. So all your measurements in the circuit are measured with reference to that bottom node A. However, if you wish, you can choose any node as your reference. You could choose B as your reference, you could choose C, or you could choose D. Does not really matter. The distance between the 2 nodes will remain exactly the same, meaning the distance meaning the difference in electrical potential. The potential difference between those 2 nodes will remain exactly the same. It will not change, meaning the voltage between those 2 nodes will remain the same. The value with your reference might change, but the voltage will not. Let me use a height analogy. My height is 5.5 feet, barely. Okay, 5 feet 6 inches. So if I measure my height and I use the floor of this room as my reference, I am 5 feet 6 inches tall. What if I jump on this chair? Chair is, let's say the chair is 3 feet above the ground. If I jump up on this chair and measure my height, now my base or my reference point is the surface of this chair. My height still remains the same, 5 feet 6. But if I say, what is the maximum height of my head as measured with reference to the floor, it would now be 5.5 plus 3. So it'll be 8.5, but my height is still the same. Make sense? And again, if I change the reference to the surface of this table, maybe it adds another feet or another foot. So now it becomes 9.5. But my height is not 9.5. My height is still the same. So the voltage between the bottom of my feet and the top of my head is still the same, 5.5. My reference node can change anywhere in the circuit, but the voltage between 2 points will never change. That's a little, that's a concept that we need to train our brains again. Okay, so node voltage analysis, we choose a reference node. That's the absolute first thing to do. It's the most important, because once you choose a reference node, meaning if I have the floor as my reference, what is the height of that floor as measured with the reference? 0. So once you choose a reference node, for the purposes of that analysis, the value of that node is equal to 0 volts. So you have eliminated 1 node. So 1 less equation. Okay. 1 node is eliminated, 1 less equation. Then If you have a voltage source in your circuit and you choose the negative end of the voltage source as your reference, meaning the negative end of the voltage source is at 0, then you automatically have the answer for the node voltage at the other end. So in this case, node B, VB, is equal to VS. We have now eliminated the second node. And so VA and VB are now known. VC and D are the only unknowns. So in node voltage analysis, if you have a voltage source and you choose the negative end of the source as your reference, you automatically have now eliminated 2 nodes from your analysis. You only have 2 unknowns left, B, C, and D. So we only need to write 2 equations. Does that make sense to everyone? Okay, so make sure you understand these concepts before you begin learning node voltage analysis, or while you're learning node voltage analysis, right? So we are almost at an end. It's less than 30 seconds left. If you have any questions, feel free to ask. Otherwise, we'll end class here today and we'll pick up again on Monday. Monday is quiz 2, and we will solve a problem about power, energy, Ohm's law, KVL, KCL, or resistive circuit analysis, basically. Combining resistors in series and parallel, and then obtaining the voltages and currents. All right, I'll bid you a good weekend, and I will see you all on Monday.